Today we have Paul Duffell with us from UC Berkeley, and I believe we're going to hear about a number of different problems in astrophysics related by hydrodynamics and some of the tools that Paul has created to solve these problems. Currently Paul is a Moore Fellow at UC Berkeley. He was a TAC Fellow there before that, and before that he did his PhD at NYU with Andrew McFadden. So that's all I got to say. Take it away, Paul.
Thank you, Dan.
And he's looking for jobs, too.
Aren't we all? No. So thank you. I'm going to be talking today about moving mesh astrophysics. So I'm a numericist. I do generally computational fluid dynamics and MHD. So that entails a bunch of different things. Part of it is developing new methods for solving the hydro equations and MHD equations on the computer. And then the other part of it is using the codes I've written to tackle a bunch of different problems all throughout astrophysics. The great thing about working on this is I never have to specialize, so I work on all kinds of different things. And so I'm going to be cheating with this talk. I'm pretending it's a numerical talk, but I'm just going to talk about a lot of different topics that I've used these codes to solve. So there'll be a little bit of it that's numerical. So the methods I developed use what's known as a moving mesh. Now, here at the CFA, that's probably not as foreign a concept as there's other places, since this is sort of the, one of the main home bases of the Arepo code, which is the cosmology code that's used to do the illustrious simulation. So I'm sure a lot of you use moving mesh codes in your research. This will be less impressive to you. That's okay. But the idea of a moving mesh code is, instead of having a fixed grid that you use to solve the fluid or MHD equations, you standard codes will have some fixed grid and then the fluid moves with respect to the grid. Instead, the codes that I've developed have some kind of moving mesh which deforms, whose computational zones can deform their shape to follow the fluid. So it's sort of like a Lagrangian approach, but it's not exactly Lagrangian, although I'm not going to get into the details of those semantics. So as an example, this is a code that I wrote 6 years ago called the test code, but it was based on the Arepo code that's used here. It was designed to solve the relativistic hydro equations. The idea was to do a bunch of different astrophysics problems with this. But the purpose of the slide is to illustrate how the code solves the hydro equation. So what you're looking at here is a well-known fluid instability known as the Kelvin-Helmholtz instability. So the red is high density and blue is low density, and the high density stuff's moving to the left and the low density stuff's moving to the right, and you have some perturbation which causes these eddies to form. But the amazing thing is how low resolution this is done at. You can actually see the individual computational zones, which are not squares. They're these polygons, or polyhedra in 3D. And they're found by doing this big, what's known as a Voronoi tessellation of the computational domain. I'm actually not going to talk about this code very much in my talk, but this is sort of just set the stage, because this connects with codes that you may have seen here. So I'll show you a little movie of this code in action. And I'm at a little bit of a disadvantage here, because most places I would go, I show a movie like this and people are impressed. But you've probably seen movies like this 100 times from Lars Herdquist or his students. Sadly, Lars isn't here. I was hoping to heckle him during my talk. But the great thing about having a moving mesh is, rather than passing fluid from zone to zone to zone, which can be a diffusive operation, you can have your mesh follow the fluid, which can maintain contact discontinuities to very high precision, and you have a lot less sort of numerical diffusion by doing this. It's not good for, it's not universally great for all problems, but it's good for a lot of problems. For example, cosmology that it's applied to. All right, so don't be afraid. This is not a table of contents. This is just the reason I put this up here is I'm here today and tomorrow. So those of you who are, if people are interested in any of these topics, you should come and talk to me, because I apply these codes to all kinds of different problems. The things I'm talking about today I'm underlining in red here. So I'm going to start by talking about a code that I wrote called Disco, which is specifically tailored towards, it's a different moving mesh where the shape of the zones is specifically tailored towards rotational flows, shearing flows. And I'm going to talk about an application I've used for this, which is gap opening in protoplanetary disks. So when the planets form, if they get massive enough, they can carve out these gaps in the disks. I'm not going to be talking about planet migration and the eccentricity evolution, although that's another topic I'm interested in. Dan is going to be sad that I'm not going to talk about circumbinary disks, but that's something that we've collaborated a bunch on before. I have some other topics that I'm also interested in, interactions between supernovae and some circumstellar medium. So this is an example of a project I just finished with an undergrad, doing a supernova colliding with a disk, and you're looking at, I should use this, one of these things. So this is just looking at pressure, so you know the supernova is right here, and the disk, you're sort of seeing the shock wrap around the disk. And then another project, the other thing I work a lot on is the dynamics of relativistic jets, and especially in the context of GRB afterglows. So when a gamma ray burst happens, after the initial burst of gamma rays, there's a long sort of sustained emission across the electromagnetic spectrum, and when you look at the decline of the light curve, what you're looking at is the sort of deceleration and spreading of a relativistic jet, and so you can kind of connect this nice physics problem of how did jets spread and decelerate to these observations. And then, actually, I'm going to be, I have my little 10-minute luncheon talk. I'm going to be saying a little bit about stuff I've done involving Rayleigh-Taylor instability, which is another fluid instability that I've done some work on in relativistic and non-relativistic contexts. And for those of you familiar with the Mesa stellar evolution code, I recently wrote a 1D model for sort of mocking up mimicking the mixing effects of Rayleigh-Taylor instability using a sort of diffusion model. But so the other thing that I will be talking about, don't worry, this isn't a table of contents. Only the red underlined things are things I'm talking about. The other thing I will be talking about is this connection between gamma ray bursts and supernovae. And I'm really proud of this project. This is something I worked on very recently with a grad student at Berkeley, she's now a Einstein Fellow at Columbia, Jennifer Barnes. So that's, the underlined things are what I'm talking about. So I'm going to do a little bit of numerical stuff, so hopefully you won't be too bored by that. But I'm going to do it as simply as I can. So I'm just going to start with Eulers Equations, which are these right here. And Eulers Equations are really just the equations of conservation of mass, energy, and momentum, or mass, momentum, and energy conservation. And so they're just conservation laws. They can all be written in this form, where U is a conserved density and F is a flux. If you want, the relativistic thing looks like this, which is, the idea is, so first I'm going to introduce to you how sort of standard grid-based codes typically solve these conservation laws, and then I'll sort of tell you how that generalizes to a moving mesh. So a standard, first of all of the code, any code that I'll be talking about today uses what is known as a finite volume approach. So rather than thinking of your grid as a collection of points, you think of it as a collection of cells or zones. So instead of saying I have sort of the density at this point and the velocity at this point and the pressure at this point, you'd say I have a certain amount of mass, energy, and momentum in each cell. And I evolve the equations by moving mass, energy, and momentum from one cell to the next. And that way you can guarantee that you're obeying the conservation laws to machine precision. This is just a little bit, it's a very small amount of notation. So this is a Spacetime diagram of a 1D hydro code. So here's my time steps. N labels the time steps, I labels which zone I'm in. And so I have U at a given time step, and I want to figure out what it is at time step n plus 1. And so how you can do that, this is just a little bit of math. So I start with my conservation law, and then just do an integral and then I can get this equation, which all this equation is saying is the amount of mass in my zone, how much it changes from this time step to this time step, is based on how much mass leaves the right face and how much enters the left face. So this is just a re-expression of the conservation law. So suitably interpreted, the point is this is an exact expression. So you might sort of, if you just looked at this to this, you might think it was an approximation, but this is an exact expression, suitably interpreted. So all of my sort of numerical approximations are housed in the question of how to calculate this time average flux through this space. So once I can calculate that, that tells me how much mass, energy, momentum to move from this zone to this zone in the course of a time step. So that tells me how to get from time step n to time step n plus 1. So that gives you your whole hydro scheme. So you can boil down this whole problem into the following. I have some density, pressure, and velocity in the left state, and some density, pressure, and velocity in the right state, and I want to know what is sort of the fluxes over the course of this time step. But that is a very well-posed initial value problem. So imagine my initial conditions are just a step function, some density, pressure, velocity on the left, density, pressure, and velocity on the right, and I want to evolve that to a future time. So it's an initial value problem that's known as a Riemann problem. And actually, for Eulers equations, there are exact solutions for every single Riemann problem. So for example, this is just an example, so density, I'm sort of plotting density here for an example one. So here's my initial condition in blue, and at a later time it looks like this. You have a shock, you have this rarefaction propagating back, and you have this contact discontinuity, which is just the initial discontinuity advected to the right. And here's a space-time diagram of my Riemann problem. So here's my shock, rarefaction, and contact discontinuity. So basically, all I have to do is come up with a solution for the Riemann problem and evaluate it right along this characteristic. And once I have that, there's exact solutions for Eulers equations, but even if you don't want to use an exact solution, there's approximate methods for solving Riemann problems. So once you've done that, then that tells you exactly what flux is going from the left state to the right state over the time step, and then that way you can update your system from time step n to time step n plus 1, so that completely specifies the numerical scheme. So you can all spend your afternoon writing Athena now. You know everything you need to know. So what happens if you have a more complicated mesh? So this is an example of a code I wrote called Disco, and actually this was, in some level this was inspired by Avi Loeb actually, because when I first visited here many years ago, well, like 6 years ago or something, and I was talking to Avi in his office, and I was talking about this sort of Voronoi moving mesh code, and he said, well, is it good at doing disks? And I was like, probably, I don't know. But he was like, you should try to work on disks. And so that sort of stuck in my head, and I thought about it, and the best way to do disks is to specifically tailor your problem to the flow you're trying to solve. Because for disks, most of the motion that you're trying to subtract off is just this orbital Keplerian flow. So you don't need this complicated, sort of really generalized moving mesh. Instead, you can have a very particular moving mesh which is tailored to the, with zones that sort of shear past each other. Okay, so let's say I have a complicated grid like this. Well, in that case, I still have a set of zones with some volume, so I can have a certain amount of mass, energy, and momentum in each zone. They still have faces. This blue face is a little bit of bookkeeping to figure out where, which zones are neighbors and what face they share. But you can still do exactly the same thing. You go to each face and you solve a Riemann problem on each face, and that tells you how much mass, energy, momentum is moving from each zone to every other zone, so that completely specifies how you update the system. But you also want these zones to move. So in this case, they're all sort of shearing azimuthally. And so these yellow faces are sort of overtaking volume. So you do need to make one more adjustment, or two more adjustments to the code in order to account for that. One adjustment is your flux. If W is the velocity of the face, you just have to make this adjustment to the flux, so you subtract off an advective component to the flux. That's one thing. The only other thing is, inside the Riemann solver, you need to, instead of evaluating along this characteristic, you need to evaluate the solution along the characteristic moving with the face velocity. Once you've made those two adjustments, you have a moving mesh code. So now you can all spend your afternoon writing a repo. So I'll give you a quick example. You probably don't have to convince you guys that moving mesh codes are good, but I'll give you a quick example that sort of illustrates this nicely. This is a pressure-supported vortex. So it's just in equilibrium, but I use a passive scalar to show the motion of the vortex. And if on the left I'm doing a fixed mesh, and it's a very low resolution, so you get all this diffusion by vecting this passive scalar. But if you use a moving mesh, oops, sorry, I did that backwards. All right, but if you do include a moving mesh, if you allow the mesh to move, you can get rid of all of that diffusion. These are you can in principle maintain these contact discontinuities to machine precision because you're just moving the face with the velocity of the contact wave. So that sort of gives a sense of what you're gaining when you use a moving mesh. Okay, there we go. Okay, this is my most complicated slide, but this is because it's MHD. So how you do MHD in a complicated moving mesh, that's a bit trickier. So the reason that MHD is generally tricky is because the simplest way to describe it is to think of the divergence constraint. You need to maintain a solenoidal magnetic field. And if you don't do that to machine precision according to the appropriate stencil, you can have a few different problems. One problem you can have is your code may be just numerically unstable and blow up. But a worse problem you can have is that it doesn't blow up, but it just gives you a wrong answer. And that's actually, one of the reasons this is so bad is because that's usually what it does. And so sort of like grid-based codes like Athena, what they do is in order to maintain the div b equals 0, they evolve the hydro variables the same way I just described before with mass, energy, and momentum in each zone volume. But for the magnetic fields, they do a sort of a lower dimensional analog of that. Instead of saying how much magnetic field is in this volume, you say how much magnetic flux is through a face. That's the variable that they evolve. The tricky part here now is I have two meanings for the word flux, because I have magnetic flux, which is magnetic field lines per unit area, and then I have flux, meaning the rate that something flows into something else. And you can also have flux of a flux, the rate the magnetic field lines cross some boundary, which is also known as the electric field, for those of you familiar with Faraday's law. But so what you have to do, in order to figure out that flux of a flux, you have to go to every single little edge in your diagram, which is a huge bookkeeping nightmare. But you go to every little edge in your diagram and determine what the electric field is on that edge, and that tells you how much magnetic flux to pass from each face to every sort of adjacent face. And that way you can maintain the divergence constraint and have a stable and reliable evolution for your magnetic field. So I'll show you a few quick code tests demonstrating how useful this is. So this is actually really tricky to come up with a code test that demonstrates that your div B scheme is working. So the scheme I'm using is called constrained transport. And so this is when I say CT off, I mean I'm just evolving the MHD scheme naively. And this is when I actually use all of those magnetic fields on the faces and electric fields on all the edges. So this particular test, it's tricky to come up with a good test that will really demonstrate this, where you turn the constrained transport scheme off and it fails the test clearly, and then but you turn it on and it passes. This I call it the magnetic flywheel. But what I do is I have some magnetic field loops here, and I have them spinning, and I have them spinning at exactly a rate so that the centrifugal force and magnetic pressure and magnetic tension all balance each other, so that this is an equilibrium. But it's totally stable, but it's numerically horribly unstable. And in fact, you can see these are errors in the magnetic field, and they grow exponentially. Not only do they grow exponentially, they grow faster the higher my resolution is. So this is clearly a numerical instability. So it demonstrates that I can at least get rid of this numerical instability when I turn my constrained transport scheme on. But this is not good enough to say that you're getting the right answer in every case. You have to do lots of tests to be sure of that. So I have a few other examples. This is a Magneto rotational instability, so it's a 3D MHD test where you're just looking at RZ plane. and it's a Keplerian orbital velocity, and I have some magnetic field threading it, and I have some perturbation at a wavelength, and I want to check that the growth rate is consistent with the predicted growth rate for the MRI. And so we passed this test, although this is a linear instability, so maybe I would still fail this test, or maybe I could still pass this test even with a bad MHD scheme, just because it's all sort of linear growth. So the real test is the sort of nonlinear phase after this has grown to be completely turbulent throughout the whole disk. And then you sort of test whether the statistical properties of this turbulence are consistent with, things that other people are getting. So the sort of standard that we chose is this magnetic tilt angle, which just measures the correlation between BR and B phi. We're able to get this consistent results with the thing. This is a test that Jim Stone's group did, Sarathi et al., which is a great MRI test, which I recommend if you really want to see if your code is doing MRI correctly. Okay, so that's enough numerical stuff. We're going to actually get to applications now. Good, I'm doing okay on time. I don't want to spend the whole time on numerics. So the first problem I ever applied this code to was planets and protoplanetary disks, in particular gap opening. So when you have when the planets form, they form in a disk of gas and dust, although I'll just be looking at the gas. And when the planet gets massive enough, it starts to gravitationally interact with the disk. And so if I put an Earth mass planet in a disk, it does this. We have a sort of a camera co-orbiting with the planet, so you're not seeing the orbital motion of the planet. But it creates this, very quickly, the gravitational force creates this sound wave, which it gets sheared out into this beautiful spiral wave shape, which I never get tired of looking at. If for an Earth mass planet, this wave is purely you can think of this as purely a linear wave that just propagates freely through the disk, right? But what happens when I put a Jupiter mass planet in? Okay, so it's a little bit different. I still have a spiral wave, but instead of being a nice linear wave, it's a nonlinear wave which shocks. You get a strong shock immediately right here, and another one right here on either side of the planet, and that shock dissipates the wave. So the wave dissipates, and then the angular momentum from that wave gets transferred to the disk. That causes fluid elements to be pushed out away from the vicinity of the planet, so it carves out this low-density annulus in the vicinity of a planet, and that low-density annulus is known as a gap. Gaps are very important for planets. First of all, they're important just from a theoretical perspective because once this gap opens, the torques that the planet feels change based on this gap. So the migration rate of the planet will change. The other thing that's important, there's a lot of things important about the gap. Another one is that the accretion rate on the planet will change, which changes the growth rate of the planet. But gaps are also important from an observational perspective because we can observe gaps. There are already observations of things like HL tau and molecular light emission where we see, low density regions in disks that we may hope are explained by planets. So if you see, so first of all, this could be a new way of discovering planets. So if you see a gap in a disk, you can go see if you can image a planet there, or you could not do that and just say you've discovered a planet. Popular, but either way, the great thing about it is the way of not only discovering planets, was discovering planets as they're forming. So you're learning about the formation of planets. So the first question I decided I wanted to answer involving gap opening is this question of, sort of represented by this dashed line, which is how big of a planet do you need to open a gap? Now, if you were listening too carefully to what I was just saying, you need it depends on nonlinearity. The criterion should be whether this wave becomes nonlinear so that you create a strong shock. Unfortunately, I was lying to you before when I said this was a purely linear wave, right? There's no such thing as a purely linear wave, right? If you look at it very carefully, there is some, no matter how low amplitude this wave is, there's some weakly nonlinear contribution to the evolution of the wave. So if I were to take little cross sections of this wave as it moves away from the planet, you would see that the wave was slowly steepening into a shock. So some distance from this planet, no matter how small this planet is, some distance from this planet, you expect a shock to form. When the shock forms, it will dissipate still. I'll show the bigger image. There you go. So a shock forms, it'll dissipate, and if the shock dissipates, then the angular momentum from the wave will get transferred to the disk. And if fluid elements in the disk are receiving angular momentum, those fluid elements got to move. So now the totally crazy thing that I'm telling you is no matter how low mass a planet is, it's capable of opening a gap. Even Earth, 10th Earth, could possibly open a gap, but over a very, very long time scale. So this planet is delivering torque to the disk through this shock, but it may take a long time before that gap opens. So in reality, it's a competition between timescales, and the main timescale competition is the planet opening the gap while viscosity is trying to refill the gap. But that's a very different criterion for saying you need a nonlinear. So if you were saying it needed a nonlinear interaction, then it's about like Saturn's mass or a little bit bigger that you need in order to open a gap. But this is based on viscosity, and we also don't really know what the viscosity is in protoplanetary disks. So if the viscosity is low enough, you could get an Earth mass planet opening a gap. So that's the statement.
Is this two-dimensional?
This one is two-dimensional, yes. This has also been done in 3D, but I can talk about that later if you're interested. I mentioned before you can describe this wave using purely linear theory, which is mostly true. You can see there's the solid curve is the predicted shape of the wave, and the dash curve, the points are density maxima. But so here's the nonlinear. So each of these plots is basically what I sort of alluded to before, where you take little cross sections in the wave as it propagates away from the planet. And the first people to predict that low mass planets could open gaps was Goodman and Rathkoff in 2001, and they did sort of a semi-analytic treatment of this wave, and predicting where the wave would shock and how quickly it would dissipate. And then 10 years later, Don Rathkoff and Stone did this with Athena, but they did a shearing box around the planet. Whenever I draw this, I make sure I draw the shearing box really small. In contrast to the stuff we did, which was a global disk. So we all were able to see the same sort of thing where we see the wave steepen and shock and dissipate. But when you do a global disk, it's much more satisfying because you can actually watch the gap open. So this is the first example where we did this, was with a 10 Earth mass planet. This is only over 1,000 orbits. So it's only 1,000 orbits, so we only just started to see the gap open in this one. But the only reason I like this slide is because it's kind of cool, because when the gap first starts to open, it actually opens as a double gap. You get one gap on either side of the planet, and that's exactly where the shock is forming. So these dash curves are the theoretically predicted positions of the shocks. But so after publishing this one, I decided to sort of follow up by, first of all, making some improvements to the code so I could run it for longer, because you need to run these for a very long time to see it for low mass planets. And then I also added viscosity to the code so that the planet had something to compete with, and this will be a movie in a second. But this is a Neptune mass planet in a viscous disk over, I think, 10,000 orbits. So each frame is like 100 orbits or something, so it's going to be very choppy. But you can see, if you wait for a very, very, very long time, slowly, slowly opens a gap. And so we were able to come up with a new criterion for gap opening. So here's the old criterion from 93, Glenn and Papalouisu. And this is also before I learned how to make good plots. But this is planet mass, and this is viscosity, basically. So you have, this is an old criterion, the solid curve that says nothing below this can open a gap. We found plenty of planets below this that could open a gap. This was later refined in 2006, but this curve said nothing below this curve could open a gap, and we found plenty of planets below that curve that can open a gap. We actually found, as long as you're willing to run the code for long enough, you could get, there's no sort of minimum planet mass, so long as you're willing to make the viscosity low and run it for a very long time. And we found this very simple It's much simpler, very simple scaling relation, dependence between planet mass and viscosity, which is just a competition between the rate that the planet delivers angular momentum to the disk and that that viscosity removes it. And so, so actually, now that we sort of actually have a total picture for how these gaps open, you know, since there's even a semi-analytic theory for how the shocks propagate, where exactly the shocks form, and the rate that angular momentum is delivered to the system, you could actually build full 1D models for these planets. This I'm just going to show you is a formula that we worked out for the depth of the gap as a function of the disk and planet parameters, and it only depends. This is a huge parameter survey with a bunch of viscosities and aspect ratios and planet masses. But this, we found that this, that you can describe them all with just this parameter, the gap depth, just using this parameter, where Q is the mass ratio, the planet to star mass ratio, H over R is the disk aspect ratio, or proxy for temperature if you want, and alpha is the viscosity. Okay, so that's planets. So now I'm going to shift gears and talk about supernovae. So hopefully I'm not giving you guys too much whiplash. Is there any supernova observers here? Oh good, you're close. Okay, excellent. Now you're on the hot seat. All right, so inside of this stained glass piece, I've hidden a supernova. Do you think you could find it? It's good, I got extra time, so.
The yellow part looks like there might be.
Yes, that's too obvious though. That's too obvious, right? So when you look at a supernova, like how do you see a supernova?
It's a point source.
Point source. Yeah, but the data you see, what does it look like?
It looks like a point source.
Just a point source. What are you saying?
Light curve.
Light curve?
What's that?
Or what else? Light curve? What else can you look at?
Oh, is this a spectrum over here?
What?
Oh,
What?
yeah, no, that's a
What?
broad
This
line.
whole thing?
Broad line. Yeah, all right.
What did you say? Who said that?
It's a broad line one.
Oh, good. That was the next question I was going to ask you. So good. Just from looking at this stained glass piece, you can identify that as a broad line 1C. Very good. Actually, that's really good. So actually, now let's for the extra $100. What can you identify? Or can you just guess? Maybe. Which broadline 1C this is?
I'm going to guess 98 BW.
That's exactly right. That's good. This is very good.
I'm keeping these up $100.
They better pay you very well here. Yeah, good. Excellent. This is 98 BW. Very good. So, so the reason you're able to identify this as a broadline 1C, why were you able to identify it as a broadline 1C?
It's got the big iron lines.
Yeah, well, it just has very broad lines, right? That's how you can tell it's a broadline 1C. It has very broad lines. So broadline 1Cs have very broad lines which imply very fast velocities of order 0.1 c, which means the sort of inferred energies are like 10 to the 52 ergs, an order of magnitude bigger than sort of typical core collapse supernovae. So that's sort of a big mystery about broadline 1Cs. But the other interesting thing, so this is 98 BW, which is the most famous of all broadline 1Cs because it's the first supernova that was ever discovered coincident with a gamma ray burst. So nowadays we know that long duration gamma ray bursts are associated with supernovae. So every time you see a long duration gamma ray burst, there's also a supernova there. And every time that supernova is a broadline 1C. So, so that's sort of a clue as to what maybe broadline 1Cs are, as they're related. There's also broadline 1Cs which are observed without associated gamma ray bursts. There's a few reasons that might be. One reason that's not favored, but I'll include it just for completeness. One reason that it might be is if this is the GRB. Oh, by the way, I can do the rest of this talk just on this slide, but I won't. Don't worry. I'll do a lot of it though. But most of this, so this is the GRB, and this is the supernova. Maybe sometimes the observer's over here and they just see a broadline 1C and they don't see the GRB. But it's also possible, and I think it's more favored, that just whatever mechanism is creating a GRB sometimes fails, but you still get a broadline 1C supernova. Or maybe they're just totally, there's ones with GRBs maybe totally different things than ones without GRBs. But the process of, but it is reasonable to think that maybe the GRB isn't always successful because it's very messy to try to get this gamma ray burst out. You're trying to get a Lorentz factor of 100 jet out of, and you know, it's created deep in the core of the star by some mechanism, probably an accreting disk on a black hole or something, maybe a neutron star. But it's created deep inside this star, and it has to punch its way through this collapsing star in order to create a relativistic jet afterwards. So the process of doing that may be tricky, and maybe sometimes it doesn't succeed, but you'd still get a supernova. But so this is to introduce a project that I worked on with a grad student at Berkeley, who is now an Einstein Fellow at Columbia, but on whether or not you can get the GRB and the supernova from the same mechanism. So in other words, this is known as a jet-driven supernova. So in other words, in the process of punching a jet through this star, you necessarily have to impart a bunch of thermal energy onto the star. And so if you impart a whole bunch of thermal energy onto the star, you can explode the star, and you can ask yourself whether or not such an explosion could look like a broadline 1c. And so this is the thing we wanted to investigate. And by the way, the code that I used, I haven't talked to you about yet, but you already see it here. It uses a moving mesh with sort of radially shear. So I could do the whole thing on this slide with these radially shearing zones instead of so it's like disco, but instead I have sort of radial tracks instead of azimuthal tracks, and it's for doing relativistic outflows or non-relativistic outflows also. And so the sort of division of labor is so I would run this calculation of a jet breaking out of a star, which has been done by many people before, but usually when you do that, you're focusing on what the jet looks like, what properties of a jet you can get out of it. But then instead, we want to look at sort of what this shock being delivered to the star sort of does to the star and how it explodes it. And so then I hand off my hydro to Jennifer Barnes, and then she runs a full radiation transfer calculation on it to get light curves and spectra to see whether that you can get a broadline 1c. And this part is really essential because you can sort of explode the thing and go, well, it looks like I get fast velocities, but until you do a full radiation transfer, it's not clear whether or not it would have been categorized as this type of supernova or that. So here's I'll show you a movie of this. So on the left, I'm going to plot log of density, and on the right, I'm going to plot nickel abundance. I'm estimating sort of nickel production by saying anytime a zone attains a temperature above 5 × 10⁹ Kelvin, I just say all of that becomes nickel. So it's a very crude approximation, but I'm just trying to figure out roughly how much nickel I get and how it's distributed in space. And so right now we're deep in the core of a progenitor star, and so I've carved out I've collapsed the core and carved out this little cavity here, and I'm going to start injecting a jet deep in there. So the energy from the jet fills up this cavity, and then it starts to punch its way out. We're going to zoom out in a second and watch the jet propagate through the stellar interior until it's about to get to the surface, and it breaks out, and then the jet is punching its way through, and you get this nice super relativistic jet. It's like about 100 Lorentz factor of about 100, and notice the nickel is distributed right along the pole like this. That's not because it's hottest along the pole, it's just because it gets produced in the core and then sort of ejected, it's carried out on the jet. And then what I do is this is all stuff that's moving at the speed of light. I ignore all that stuff and I zoom in. Here's stuff moving at 0.1c, so I sort of zoom in on this and then I hand it off to Barnes. And then she does all the light curves and spectra. So here are some light curves that we were able to produce. These solid curves are the light curves, and we didn't get things quite as bright as 98 BW, unfortunately, but this is so far just a proof of concept. But we get things that are reasonably consistent with existing broadline 1Cs, and then we have spectra at different viewing angles. So the blue is viewed on axis, and the red is viewed off axis. And so one of the cool things is that there is a little bit of a difference depending on whether you're viewing on axis or off axis. The lines are a little bit broader, so you would infer a little bit faster velocities. And so this is a comparison with, so the other thing is we don't know is, would this be classified as a broadline 1C? So we used, we also had Mariam Mojaz and her grad student Yutsun Liu, and she did, they basically, so they're observers, so they took our supernova and tried to classify it as if it was a supernova that they'd observed. And so they use this, what's known as the Snipcode, which sort of compares it with other existing supernovae. And so these are sort of our best matches. And if you think this is too good to be true, you have good instincts. But the reason it looks so nice is because the way the code works is it first subtracts off the continuum and then just matches the lines. And then we added the same continuum back, so it looks very nice. But the point is that the lines are matched with existing broadline 1C supernovae. So this would have been classified as a broadline 1C. So that's basically all of that. I've ended with plenty of time for questions. That's good. But the point is, this is a sort of proof of concept that it is possible actually to get this type of supernova with a jet-driven model. But we still need to sort of explore how robust that is by sort of varying what our progenitor model looks like and improving some of the physics, which we did, crudely just to get this basic picture. So I guess I can just conclude here and say moving mesh codes are very fun, and they're great for solving all kinds of problems in astrophysics. They're not just for cosmology. But for problems, a lot of problems in astrophysics, like disks and jets, you don't have to use this arbitrarily sort of moving mesh. You can sort of tailor, it can be very advantageous to tailor your grid to follow to subtract off a particular type of flow. So that's it. Thank you very much.
So on that last point, of course, and I'm not saying this is my opinion, but
yes,
someone in Lorenzo's group might say, if you use a repo, you subtract off any flow automatically.
Yeah.
Because it's Lagrangian in that sense that you follow the mass.
Yes.
What would your response to that? Like, why is your method better?
Well, I'm not saying it's better. I'm saying this is a problem-dependent statement, right? For some problems, it's much better to subtract off as much of the advective part of the velocity as you can. The main part you want to subtract off is the supersonic motion. That's the most important thing. So for disks, if you just subtract off that Keplerian orbital motion, you've basically you subtract off almost all of your vection errors. But the trade-off with using a totally arbitrary mesh is that you have these arbitrary zone shapes, which can sort of introduce numerical noise into the problem. So, for example, if I tried to do the disk with this, you could do it, but you're inherently going to have a little bit of noise. Even if you're just trying to do a Keplerian disk with nothing else interesting going on, it's a lot harder. You'll converge much slower than if you have a shearing code like Disco. So this is sort of the justification for doing that. But it's totally problem dependent. There are some problems it's better to have a completely general mesh.
Is the computation time much different between allowing a general mesh versus a fixed?
So for me, that depends on who you are probably. For me, in my personal experience, the computation time is much faster for Disco and the jet code than it is for the code I wrote here. But that just might be because I'm not very good. It may be the case you can optimize this just as well. So I'm not going to say that it's that's an issue.
No, I think you're being modest. I think it's true. So like codes like a repo are intrinsically very slow, right? I mean, per cell, way slower than something like that.
So a week ago or a couple of weeks ago, we heard the talk by Anna Fregel. She observed the early stars that show some element balances that indicate that those were ejected from the central part of the supernova, while the only way to explain it is with the jet, actually, that pushes those out. while the rest forms a black hole, like the iron ends up black. And it would be very interesting if you were to apply your run to that case. You haven't tried to consider the abundances that one gets out of these explosions.
No, I mean, certainly, this is one of the great things about this is it's great at tracking things like that, right? It's also true of a Raper, right?
So that would be very, you might want to look at her data, because so far it was hand-waving arguments that a jet is necessary in a population of 3 star to make the abundances that she sees.
Wow, I did not realize.
The other question I had was about the 2D plot.
Yes.
So how do 3D effects?
Yes, that's a great question. Oh, that's good. That's a great question. So I'll get to you. It's okay. We have plenty of time for questions. So.
Can you make 3D stained glass?
Yeah, I'm still working on the 3D stained glass. But so you might say, okay, well this is 2D, so I'm not considering the actual physical scale height of the disk. So maybe the case the temptation might be, well, this might be all wrong because if the planet's, you think of the planet's Hill radius as its radius of influence. If its radius of influence is smaller than the physical scale height of the disk, then how am I clearing a gap with a planet like that? So that's one of the reasons that this sort of nonlinear criterion is also the same as the criterion of whether the hill radius is larger than the scale height. It's one of the reasons that's a very popular criterion. But, so there's 2 things I'll say about that. One is 3D has been done before, and they found, amazingly, if you just vertically integrate 3D disks, they're exactly like 2D disks. They just take a lot longer to run. But it's actually really, I expect it to be a little bit different. But the reason is, all of these arguments are exactly the same in the 3D disk. The real radius of influence is this shock, which is, we know that the linear wave behaves exactly the same in 3D, basically exactly the same in 3D. And so the propagation of the wave and steepening into a shock will still happen in 3D. And so that angular momentum, those angular momentum arguments will still apply in 3D. And so there will be sort of a bunch of vertical motions and sort of things, but in the end, all these angular momentum arguments sort of end up being robust in 3D.
But it's good to know because this also is relevant for black hole binary.
Yes. Yeah, absolutely. Wait, did you have that was the second part.
So related to Benedict's question, I was wondering in the test code, do you use any criteria for regularizing your?
Yeah. So basically, I basically do the same thing that was in the Arepo paper, and it's a little bit, it's a little. I think that there was maybe a couple of years ago there was a paper on sort of making mesh regularization in a sort of way that reduces a lot of the grid noise, and I think. So now that Arepo is probably much better than mine at the regularization because I haven't gotten around to implementing that in mine. But yeah, it's amazing how nice it works if you can just steering the zones, giving them a little bit of velocity towards their in order to make the mesh generating point at the same as the cell center.
And in Disco, and especially the outflow code, are there any similar analogous criteria that you have to enforce?
Not really, other than sort of zone aspect ratios.
Yeah.
But that's easy. That's way easier than any of that stuff because you can just cut a zone in half or merge it with its neighbor, and so that's extremely reliable. Yeah. Sorry, behind you.
So my question was somewhat related to looks. I'm used to thinking of the gap of the cell face being shared by only 2 cells, but I'm wondering what type of conditions you put on the sizes of your cells so that you don't have many cells overlapping. Because it seems like 2 cells do share a face partially, and that introduces extra code.
I'm not sure what you mean.
So I'm used to, on what I mentioned, when you have a face, then I have to compute the flux or magnitude.
Yes.
Only on that face, and it's only shared by 2 cells.
Yes.
But when you have 2 cells that partially overlap,
I'll
have to compute that for 2 smaller faces versus just 1.
This is not, this aspect is not that different from Arepo. So like you're saying, I have a zone here, which is this guy's neighbor, and then I have another zone right behind him, which is also the neighbor.
So I'm thinking the 2 gaps. If you have cells that are very different sizes, you have density differences.
Yeah, this doesn't matter that much because almost every numerical operation I'll weight by the surface area of the face. So if a zone just shares a little bit of area, it doesn't contribute much. So there's no issue with large numbers. I mean, in a rainbow is also, if you don't have a regularized mesh, of course, you can have a huge number of neighbors. But even with a regular mesh, you'll have occasionally some zones that have lots of neighbors. In this, usually what I'll do, for disco especially, what I'll do is I usually will have all of the zones in the annulus sharing the same velocity, and that will mean that basically this guy only has 2 neighbors outside at any given time. But I found that it actually doesn't really matter. That doesn't really affect things numerically to have a whole bunch of neighbors. The only thing that affects things is if your neighbor has a very different aspect ratio than you. So that's the thing that'll hurt you. But by sort of putting criteria on how big of an aspect ratio a zone can have, then you can sort of prevent that. So you were first, I think.
No, I mean, this was just a small question, but there must be like trade-offs here between allocating and reallocating memory as your mesh adapts, and actually the sort of CPU cycles of updating the zones. And I don't know, going forward, how do you think that's going to change as we're becoming sort of more and more memory bounded?
That's a good question that I don't really know the answer to. So I would say, yeah, I mean that this is something worth considering, is how much memory are you taking up with a mesh like. With this mesh, you don't end up taking up a lot more memory than you would otherwise because, well, until you do MHD, then you have to have information stored on every single face, and so that can be like a lot of memory potentially. But I don't even with this, the memory overhead, isn't like an order of magnitude bigger than it would have been if I just had a fixed grid. So I'm not too worried about that, but yeah, I mean, I guess I just always think of computers as just infinite things and not don't worry about memory. But
It's a good assumption in the long run.
in the long run, yeah, I try to think future.
The computer will get bigger. You don't have to worry about it.
Yeah.
The whole power plant.
Do you have self-gravity in your code?
There is actually a version of this code that has self-gravity in it that was written by a grad student at NYU that is not in sort of the official version because I haven't even tested it. But I mean, how I look at it is when I only add something into my code if I'm going to specifically use it on a problem. So I haven't yet done a problem with, that requires self-gravity, but there are definitely ways of doing it. This student, I think, used a sort of an approach that did a Fourier transform in the phi direction and then solved the equations in the RZ plane. But yeah, I don't know it that well because I didn't write it, but yeah. Are there other questions?
These are all publicly available codes.
This one is. Oh, I only do it when the code's good enough. The other ones are still, I have to take all the stupid comments out. But yeah, they're all. I'm not opposed to people using them. I wait until I'm sort of happy with how the code is, and then it's publicly available.
All right. Well, we've got 5 minutes left to take a break.
Just okay.
Yeah, we can all sit here in silence for 5 minutes.
Or discuss politics.
We could discuss our religion. But yeah, and if you're interested in coming to dinner tonight, you probably have a few spots open, so let me know. And let's thank Paul again.
Well, nobody's ever complained for talking early.
Excellent.
Oh, thank you.
Thank you, Paul.